So this would be ane, 1, 2, 3, 4, 5, so that's pentane. It's got 2 methyls, so it's dimethyl. And then whether I go left to right or right to left, this would be carbon 1, 2, 3, 4, right, 5. So it'd be 2, 4. And if I went the other way, it'd be 1, 2, 3, 4. So it doesn't matter. So this would be 2, 4 dimethyl pentane. If I had this compound, let's say I had a Br, a Cl. So those are compounds having that are Rx, where X is a halogen. These are called haloalkanes. So that would be in your sheet that I gave you guys on functional groups. Those are haloalkanes. In the bad old days, they were called alkyl halides. That's really not an IUPAC term. So in a case like this is also, since it's a haloalkane, I'm going to write ane as my base name. It's got 1, 2, 3, 4, 1, 2, 3, 4, 5. Geez, a bunch of pens here. So this is a pentane. It's got bromine and chlorine, so it's a bromo-chloro-pentane. So when we're dealing with the halogens, we take off the INE. So the halogens are all called, so they're called halenes, right? So it's bromine, chlorine, fluorine, iodine. We're going to take off the INE and replace that by O. So bromine becomes bromo, chlorine, chloro, fluorine, fluoro, and so on. So this is a bromochloropentane. And again, we put the B before the C, we alphabetize. But this one is interesting because if I go left to right, my locants are 2, 4. If I go right to left, my locants are 2, 4. So the question is this 2 bromo, 4 chloro, pentane, right? 2 bromo, 4 chloro, or is it 4 bromo, 2 chloro? And the answer is in a case like this, since it's the same sum of the locants, 2, 4, or 4, 2, we let the one that's written alphabetically first get the lower number, right? So I'm going to call this 2 bromo, 4 chloro, pentane. Right? So 2 bromo, 4 chloropentane. So in a case where the sum of the locants in both directions is the same, you want to give the lower locant to the first prefix, the one that has the letter that's higher up in the alphabet, A, B, C, not the one that's lower down the alphabet. Okay, so since the B precedes the C, the B would get the lower locant, right? It would get the 2 bromo, not the 4 bromo. Okay. If I have cycloalkanes, and I think we talked about this briefly a while back. If we're dealing with cycloalkanes, so if I have something like this, then it's cyclopropane because it's an alkane. It's only got carbon-carbon single bonds and CH bonds. So it's an ane. It's got 3 carbons in the ring, so it's prop, and it's a ring, so it's cyclo. So that's cyclopropane. And then if I had this, which is 4 carbons, that's cyclobutane. If I have this, that's cyclopentane. And if I have this, that's cyclohexane. Right? So ane, carbon-carbon single bonds and carbon-hydrogen single bonds only. If it's a ring, it's preceded by cyclo, and then there is a prefix for the number of carbons in the ring. Well, what if we have substituents on the rings? So if I have this compound, what do I call that compound? Well, that's a cyclopropene, but it's got a methyl group on it. So I'm just going to call this methyl. Oops. I'm going to call this methyl cyclopropene. Now, I'm not going to give it a locant because it's understood that whether I put the methyl on this carbon, or that carbon, is the equivalent compound. Right? So, and that's the thing with IUPAC. IUPAC wants you to give just enough information to name the compound unequivocally, but no more information. So if you give superfluous information, right, then the name is wrong. So if I call this 1-methyl cyclohexane, well, I don't need the 1 because if all I have is one substituent, it does all 3 of these carbons are equivalent, right? 1, 2, 3 are equivalent. If I put the methyl here, here, or here, I make exactly the same compound. So the 1 is superfluous. That compound is methyl cyclopropene. But what if I had something like this? What if I had something like that? Well, that's a cyclobutane, but it's got a methyl group and an ethyl group. So this is an ethyl, methyl, cyclobutane. But it's one of many ethyl, methyl cyclobutanes, right? And I should have done that earlier. I could have them both in the same carbon. I can have them on adjacent carbons, or I can have them with one here, one there. Okay, so there's several different ethyl-methyl cyclobutanes. Now, they're on adjacent carbons. So somebody's going to be 1, and somebody's going to be 2. So the sum of the locants will be the same. So the question then is it 1 ethyl, 2 methyl, or is it 1 methyl, 2 ethyl? And I think I kept, yeah. So we're going to use the same rule we did with this one. If the sum of the locants is the same, regardless of the direction you pick, then we're going to give the smaller locant to whoever is higher in the alphabet. Right? So I'm going to call this 1 ethyl. We call it 1 ethyl, 2 methyl cyclobutane. Okay? Now again, so the way I do this is I write out my base name, get my length of my carbon chain, write my substituents alphabetically, and then hunt for locants. What if we had this? What if I had that compound? Well, that's a cyclopentane. But it's not just a cyclopentane. It's not just a cyclopentane. It's got a bromine and an ethyl and a methyl. So this is a bromo, ethyl, methyl, cyclopentane. So I need locants. Well, I want to get the smaller sum of locants. Because in this case, see, whether I'd gone 1, 2, or 1, 2, I've gotten the same number, right? The same supplement 3. But if I number, let's say I number, let's say I start here, and I go, let's see, so I can go, if I go clockwise, I'll have 1, 2, 3, 4, going clockwise, which gives me a sum of 8. If I go anti-clockwise, it's 1, 2, 3, 4, which is right, still the same sum of 8. I'll write that down too, so I can have 1, 2, 3, 4. Or, let's see, I could have, if I call this carbon number, that's what bromine is 1. If I start with the methyl as 1, I can go 1, 2, 3, 4. So the bromine as 1, so bromine as 1, my sum is either going to be 8 or 8, right? So 2 8s. If I pick my ethyl as 1, if I go clockwise, I'll have 1, 2, 3, 4, 5. So that's not good. So it'll be 1, 2, 3. So that's 3 and 1 is 4. 4 and 5, that's 9, right, which is higher. If I go this way, it's 1, 2, 3, 4. So I'm going to write that down. So if I start with this as 1, I can go 2, 3, 4. So the ethyl as 1. So the ethyl as 1, I have 1, 2, 3, 4. That's a sum of 7. That's a sum of 7, right? 1, 2, 3, 4. That's a sum of 7. Okay. Now, with my methyl as 1, if I go clockwise, I'll have 1, 2, 3, 4. So 1, 2, 3, 4. So with my methyl as 1, right? I'm going to pick a different color, like blue. So my methyl is 1. I'm going to have 1, 2, 3, 4. So that's 1 and 2 is 3, and 4 is 7. So I'll have 7. And then obviously, it won't be as good if I went clockwise, right? Because that's 1, 2, 3, 4, 5. So that's not good. So the smallest sum of locants arrive with either ethyl as 1, which is in the red, or methyl as 1. And they both give me the smallest sum of the locants. So since it's a bromo ethyl methyl, here's what we're going to do. I want the number in front of the bromo to be the smallest possible. So if I went, so what do we do now? Ethyl is 1. So I'm going to take off the, so I'm looking at red. So I'm going to take off the green and the black. Green and the black come off. I'm keeping the blue and the red. I'm keeping the blue and the red. Okay. So if I numbered this way, I'll have a 1 for the ethyl, 2 for the methyl, 4 for the bromine. If I numbered this way, I'll still have 4 for the bromine. So it's a wash for the bromine. Who is next? Ethyl. So if I number this way, then the ethyl gets 1. Whereas if I did it this way, then the ethyl gets 2. So I'm going to go with the red, because that gives the bromine the smaller number, which I would have got in both cases. But now it gives me the ethyl the lower number. So I'm going to call this 4-bromo. So it's 4-bromo, 1 ethyl, 2 methyl, cyclopentane. Okay, so numbering so that I'm looking for the smallest locant, the smallest sum of the locants. And if I've got 2 sums that are the same, I want to give the first substituent the lowest possible locant. And then if it's a wash, I want to give the second substituent the lowest possible locant, and so on and so on and so on. And you couldn't possibly have a case where you only have 3 substituents and they were equivalent numbers for both. Because if it is, it means they would have been just one name if going clockwise and anti-clockwise are the same, right? Okay, so it's 4 bromo, 1 ethyl, 2 methyl, cyclopentane. Okay, let's name. So that's alkanes. Let's name this compound. Name that one. So again, this is an alkane. It's a haloalkane. So I'm going to write ane. My longest chain. Oh, actually, let's make it more interesting. 1, 2, 3. No, that's not what I had in mind. But whatever. So it's an alkane. It's not just an alkane, it's got a bromine, 2 chlorines, and a methyl. So this is a bromo dichloro methyl. Oh shoot, I'm sorry. My chain has 1, 2, 3, 4, 5, 6 carbons. So this is hex. And now my substituents are bromine, 2 chlorines, and a methyl. So it's bromodichloromethyl, hexane. I need locants. So if I number left to right, I'll have, if I go left to right, I'll have 2, 2. So 1, 2, 2, 3, or 5. If I number right to left, I'll have 1, 2, 3, 4, 5, 5. Clearly this should be bigger. That's 10, 16. This is 12. So this is going to be 3 bromo, 2, 2 dichloro, 5 methyl hexane. What about this compound? That compound is an alcohol, right? This is ROH. And the base name for alcohols is all. So I'm going to write all. Now this is where it gets a little bit different. So in the case of the alkanes, cycloalkanes, and haloalkanes, our root name was ane. And our next question was, how long is the carbon chain, right? The longest carbon chain. That was the most substituted. And that would have been hex, pent, oct, whatever. With alcohols, before we get to the length of the carbon chain, we're going to ask another question, which is, what is the character of the carbon-carbon backbone? In other words, we're asking, is the backbone saturated? In other words, is it only carbon-carbon single bonds? And if it is, then the backbone is an and. If the backbone contains carbon-carbon double bonds, it's an N. And if it's got a carbon-carbon triple bond, it's an in. Actually, I tell you what, let's Yeah, let me sort this a little bit. So let's not do the alcohol yet. You come back to that one. Let's just go ahead and do some alkenes and alkynes. So let's name this compound. So that compound has a carbon-carbon double bond. So even if it has carbon-carbon single bonds as well, if it's got a carbon-carbon double bond, it's going to be called an alkene, because the alkene takes precedent over the alkyne, or over the haloalkene. Good call. The alkene takes precedent over the alkene. So my base name is going to be ene. I'm going to ask how long is my carbon chain, and it's got 1, 2, 3, 4, 5 carbons in it, so it's a pentene. But there are lots of different pentenes, right? I can have a pentene like this, I can have the double bond here, and so on and so on and so on. So I need to separate my pentene from all the others with a logo. Now, unlike the other cases where the substituents were on a single carbon, in the case of the vanillic group, it spans 2 carbons. So which number do I use? And the answer is, as you might think, the smaller number. So even though the double bond is spread across carbons 1 and 2, I would call this 1 pentene to indicate where the double bond starts, and I want the smaller number. There is some freedom in that it can either be called 1 pentene, or it can be called pent 1E. And I should tell you, IUPAC, ever so often, I don't know, every 5 years, I think, gets together and they re-examine the rules of nomenclature. And I think recently they revised it, and there's a preference for putting the 1 in front of the E directly, rather than what was allowed back in the day. So for our class, either option is fine. So either 1 pentene or pent 1E, either one is fine. But I think there's an increasing push from IUPAC now to use this version. So this is 1 pentene. What about this compound? What would I call that one? So let me just write this. What would I call this compound? Well, again, this is an ene. It's got 1, 2, 3, 4, 5 carbons in it, so it's a pentene. The double bond is, if I number from left to right, is 1, 2, 3 is where it starts. If I number right to left, 1, 2 is where it starts. So this is a 2 pentene. Or I can call it pent 2E. But it turns out there are 2 different pent 2Es. There's this one, and then there is this one. Okay? And as you might guess, in this one, I've got H's, which find themselves on opposite sides of the double bond as a frame of reference. So I'm going to call this trans pent 2E, or trans 2-pentene, and typically that's put in parentheses. Whereas in this one, the 2 H's are on the same side of the double bond as a frame of reference. So this is called cis 2-pentene, or cis pent 2E. Let's name this compound. So I'm going to call this ene. But if you look at the compound, So I'm going to call it ene. But if you look at it, it's got two carbon-carbon double bonds. So I'm going to call it diene. And now I want the longest carbon chain that includes the major functional groups. Because if I look at the longest chain, that's going to be 1, 2, 3, 4, 5, 6, 7, 8 carbons. But the chain, the longest chain that contains the major functional groups, which in this case are the 2 vanilla groups and the chlorines, the longest chain is 1, 2, 3, 4, 5, 6, 7. So I'm going to pick my longest chain, right, as this, as my longest carbon chain that contains my major functional groups. In which case, the 2 chlorines and this group are relegated to being substituents. Okay? So how long is my longest chain that contains my major functional groups? 1, 2, 3, 4, 5, 6, 7. So that's going to be a hept. Now, when I have 2 consonants like this, I'm going to insert an A, just because it's easier on the tongue, I guess. I'm not making this stuff up. So this is a heptadiene. But it's not just a heptadiene. It's got 2 chlorines and this group. So what is this group? Well, if you notice, it's got 1, 2, 3, 4 carbons in it, so it's a butyl. But butyls come in different flavors. There's a normal butyl, there is isobutyl, there's sec-butyl, and there's tert-butyl. This one is iso because it has the gem dimethyl group. It's got 2 methyls on the same carbon. So this is a dichloro isobutyl heptadiene. Now, remember with butyls, the iso, you use the I in iso in alphabetization. You don't for sec, you don't for tert, but for iso you do. So this is important because if you just said butyl, B of butyl beats C of chloro. But because this is isobutyl, C of chloro beats I of isobutyl. So this compound would be a dichloro isobutyl butyl heptadiene. What I want the locus. And because the alkene is highest priority, I'm going to give these locants the smaller number. So this is 1, 2, 3, 4, 5, 6, 7. And I will call this compound 6,6 dichloro 3 isobutyl 1 4 heptadiene, or 6,6 dichloro 3 isobutyl hepta 1, 4 diene. So either one of those 2 names would work. What if I had, oh, no, we're not done. Yeah, we're not done. Whenever you have carbon, wow. Whenever you have carbon-carbon double bonds, you want to look out for the possibility of isomerism. And in fact, we talked about this in a lecture beforehand, but let me just spend another couple of minutes on it. So under what conditions would we get isomerism in an alkene? So if I have an alkene like this, where I have two of the same groups on any one of the vinylic carbons, so either two H's or two chlorines, it doesn't really matter, then even if I flip the chlorines, or if I flip, in this case, the H and the ethyl, let's flip those. So I'm going to have H and the ethyl. Those are the same compound, right? Because in this, I have an H that is cis to a chlorine, trans to a chlorine. And it's on the same carbon with an ethyl. Right? Same compound. So if I have the same two groups on any one of the vinylic carbons, geometric isomerism is not possible. On the other hand, if one of these was a bromine, and I flipped the H and the ethyl, well, now these are different compounds, right? Because in this case, the H is cis to a bromine, and it's trans to a bromine. The H was trans to a chlorine, and was cis to the chlorine. Okay? So geometric isomerism is possible when neither vinylic carbon has the same two groups on it. If any one of the vinylic carbons has the same two groups, geometric isomerism is impossible. So that's the first point. So now, when I look at this compound, right, this had two H's, so there was no cis or trans possibility. This one had two different groups. It has methyl and H, those are different. This has ethyl and H, those are different. So geometric isomerism is possible. I got a trans and a cis. When I look at this one, this vinylic site is incapable of geometric isomerism because I've got two H's, not an option. But this one, on this carbon, has an H and this crack. This carbon has an H and that crack. So neither carbon of the 4,5 site